This is problem number 5C for the sample test problems for test number 2. An observer on the ground notices a plane off in the distance that is flying in her direction. She knows that planes on that route generally fly at an altitude of 30,000 feet. When the angle of elevation from the observer to the plane was 45 degrees, that angle was changing at the rate of 0.5 degrees per second. How fast was the plane flying? Hint, change degrees per second to radians per second. Okay, so let's draw a picture here. I'm going to put my observer right there on the ground, straight up, and then out here somewhere is the plane. So observer is O, P is plane, and she is looking straight at the plane as the plane flies towards her. So let's see if we can get some of these numbers into the problem. The planes generally fly at an altitude of 30,000 feet. So I think it's safe to assume that the height here is a constant 30,000. And then it talks about the angle of elevation from the observer to the plane. So from the observer's perspective, she's looking up and seeing that plane off in the distance. It is very tempting to think that that is the angle of elevation. It is also very wrong. Angle of elevation always means point straight ahead and then point to the thing you're looking at, and it's the angle between those two pointers that is the angle of elevation. So from her horizon line that's in black straight ahead, her head has to tilt up at that angle. That's the angle that we're talking about. The angle of elevation is this angle. Okay, it's not super useful that that angle is outside of my triangle. So can you figure out where that angle belongs? If we're going to put a theta somewhere in this triangle, where should it be? And hopefully we know something about geometry. Some fancy geometry phrases maybe will come back to memory. If you can draw a Z, then the two angles that you've cut out are called alternate interior angles. And if you have parallel lines cut by a transversal, then those angles are equal. So however you do it, hopefully get a theta in the picture here. Alternative to that would be to just make your right triangle come over here, and then you don't have to worry about this thing. Okay, so we've got theta in the picture, and we've got a right angle here, and then we'll start writing some things down. So we know that when the angle is 45 degrees, when theta is 45 degrees, okay, but immediately we're a little bit worried because all of calculus is done in radians, so we convert that right away. 45 degrees is pi over 4. So when theta is pi over 4, the angle was changing at a rate of 0.5 degrees per second. So symbolically, we got to write this rate of change of the angle. That's a d theta dt. It's equal to 0.5 degrees per second. But again, the same warning bell is going off. So let's convert that quickly to radians per second. So multiply this thing by pi over 180. That's pi radians in 180 degrees. And so when we smush this together, we get pi divided by, and I think that becomes a 360 down there. So this is now pi over 360 radians per second. And what are we trying to find? Let's see. We're looking for how fast the plane was flying. Well, we don't have anything in our picture yet that indicates how fast the plane is moving. I do know that the plane is going this way, so it sure feels like I should give a name to the length of that line segment. So the whole thing from here, wherever the plane currently is, to straight overhead, it's going to call that d for distance. And so ultimately, given the theta and the d theta dt, we're trying to find, let's see, the rate of change. How fast is the plane flying? So I guess that means dd dt. That's going to give us the velocity. It's a change in distance with respect to time. Okay, so we've got a good picture. We've got lots of things set up. Now we need an equation that relates everything in our picture. It is tempting to just take any right triangle and try to apply the Pythagorean theorem to it. It's not wrong, but it's not particularly helpful in this problem because there's nothing asked of us about that hypotenuse, nor is there anything given to us about that hypotenuse. I suppose you could fill it in by using Pythagorean theorem, but having something like this here doesn't seem particularly useful to me. Doesn't give me any more information about theta, and that's an inherent part of this problem. So let's get rid of all that stuff and try to come up with another relationship in this right triangle. And hopefully we start thinking of trigonometry, the trig functions. So which trig function is going to relate the d and the 30,000 and the theta? And let's see, you can use SOHCAHTOA or however you think of it, but I think tangent is the winner in this case. Tangent of theta is opposite over adjacent. 30,000 over d. Super. Here's the equation that relates theta and the d. Notice it didn't involve the hypotenuse at all, so Pythagorean theorem is really just something that might sidetrack you, but I don't think it goes anywhere. And now we're going to take a derivative of both sides of this equation. So I'll copy it again, and then we'll put the d dt symbol. So in front of both sides, taking a derivative with respect to t, d dt. Okay, let's take our derivative. Derivative of tangent of theta. Derivative of tangent is secant squared. But theta is not the independent variable, so again, the chain rule comes in and says multiply by a derivative. d dt, derivative of what? In this case, theta is the letter that we're taking a derivative of, equals derivative of the right-hand side, 30,000 over d. Feel free to use the quotient rule if you want to. Feel free to bring that d upstairs as a d to the -1. For me, I've got a rule memorized. I think some of you might have it memorized too. Negative the constant over d squared. But that's not done because d is not the independent variable. So we need to multiply again. Chain rule says multiply by the derivative of the stuff. The stuff in this case is the letter d. Okay, super. So what are we after and what do we know? All right, we're trying to find d dt. Green is not the highlighter of choice. We're trying to find d dt. There it is. So everything else in that black equation needs to become numbers. So let's start replacing the stuff that we know. Secant squared of, how much is theta at the moment in time we're freezing this thing? Well, it's given. It's in purple right there. It's 45 degrees, but again, in calculus, let's do radians. So it's secant squared of pi over 4 times d theta dt. Hopefully that's given. It says it was 0.5 degrees per second, but we got to change that to radians per second. So that's a pi over 360 radians per second equals negative 30,000 over d squared, pause on that, times d dt, which is again the thing that we're after. So if somehow we can figure out what d is, we throw it in the blank, and then it's just an algebra problem. Okay, so do we have d given to us anywhere? I don't think so. So let's go back to fundamentals, that diagram in the top left. Now we get to freeze the picture at theta is 45 degrees or pi over 4. So we're going to plug 45 degrees or pi over 4 here. And then in that particular fixed right triangle, I think we can find d. In fact, maybe the place to go is that equation right there, because that's the one that tells you how to find d if you know theta. Well, let's get rid of some of this stuff and come down here, and we're going to rewrite this equation. And instead of theta, we know that theta is 45 degrees or pi over 4, and that's equal to 30,000 over d. And now we can find d. So let's see, we're going to maybe cross multiply or multiply both sides by d. So we get d tan pi over 4 is 30,000, which means that d is 30,000 over tan of pi over 4. The good news is tan of pi over 4 is a nice number. You can use your calculator, but I'm hoping that you can figure this one out without. So pause the video if you want a moment to think about it. But tan of pi over 4 is just 1, so this is really just 30,000. So we get to take 30,000, which we've just figured out is the value of d at this moment in time, and plug it right in there. So in purple, 30,000 goes there. Okay, and now we've got to just clean this up a little bit. Again, you can bail out and use the calculator at this stage. I'm going to go a little further before we touch the calculator. All right, secant squared. If I'm not using the calculator, or even if you are, there's no secant button on there, so better know how to rewrite that. That's 1 over cosine squared. Do not, under any circumstances, think that the pi over 4 gets flipped over. It's the cosine that goes downstairs. The angle doesn't get flipped over. That's times a pi over 360. And we can clean this up on the left-hand side because I've got a 30,000 upstairs and a couple of them downstairs, so cancel one of them. And then d dt is just waiting here for the smoke to clear. Okay, cosine of pi over 4, that's actually a nice number. Cosine of pi over 4 is 1 over root 2. So this guy becomes 1 on top. That's the one that you see in the on the screen right now. But cosine is a 1 over root 2. And it's being squared because it's cosine squared. You could also write cosine of pi over 4 as root 2 over 2. Either way is fine. Okay, and we'll persevere a little longer without the calculator. Stuff is about to get nicer. 1 over root 2 squared is 1 over 2. 1 over root 2 squared, yep. And then times pi over 360, and then that's still negative 30,000 dt. And then just about done. Instead of dividing, let's see, we have a 1 divided by a half. That's really a 2. So this whole thing just becomes 2 times pi over 360. And how about at this stage, maybe we'll bring that negative 30,000 over to this side. Oh, somehow I think it moved. Wasn't it on the bottom? It was. Thanks for catching that. So it's a 1 over, 1 over. And so if I want to move the 30,000 to this side, it becomes a multiply. So negative 30,000 is here, and that's finally equal to d dt, which is the thing we've been after the whole time. So I suppose you can reduce the 2 and the 360 if you want an exact answer. I'm content to let the calculator finish this one for me. Okay, so multiplying these things together, 2 pi divide 360 times negative 30,000. Okay, so d dt is that number, negative 523.6. Okay, the negative maybe is a little bit scary, but we can handle that later. Let's get the units down here. So the units for my derivative are just going to be the units for d, distance, divided by units for t, time. Distance in this problem was given, the only distance in the problem was the 30,000 feet. So that must be our unit for distance. And then the time in this case was, let's see, we had degrees per second. So seconds is time. So negative 523.6 feet per second. Why is it negative? I thought distance is supposed to be positive. Well, look at the picture. What is happening to that green line segment as the plane flies closer and closer to our observer on the ground? The green line segment is getting shorter. So of course it makes sense that d dt is negative, because a negative derivative means the thing itself is decreasing. And yes, the length of that green line segment is decreasing. So I think that makes sense, the negative. And you don't need to convert this, but feet per second is not a typical way to think about a speed for a plane. So if you are so inclined, you can convert it to miles per hour. Maybe pause the video for a moment here if you'd like to try that on your own. And so for me to convert to miles per hour, first I'm going to get rid of feet. So I feel like I need feet on the bottom and then miles upstairs. And the conversion here is 1 mile for every 5,280 feet. And so that will let us cancel the feet. So now we're at miles per second. And then we're trying to go from seconds to hours. So I'm just going to multiply by another couple of fractions here. So I don't want seconds and they're downstairs. So I guess we need seconds upstairs, and then I can go between seconds and minutes. 1 minute has 60 seconds. So that cancels the seconds, which leaves us with miles per minute. And then one more multiply. Let's see, we don't want minutes downstairs, so we'll put it upstairs. And then we can convert between minutes and hours. 1 hour is 60 minutes. And then minutes cancel. So I think we've got everything good. We're just ready to do the calculation, and whatever we get will be miles per hour. So we're taking that number, we are multiplying it by 1 divided by 5,280. And then we're multiplying it by 60 over 1, and then multiplying it by another 60 over 1. So all told, about 357 miles per hour.